Hi, this is our fourth video in Unit 5, and it's the introduction to the quantum mechanical model of the atom. What you should have in front of you is this PowerPoint, as well as a calculator and a pencil. So be ready to do some calculations. Okay, so what we learned from the very first video in this unit is that light can act like a particle and it can act like a wave. So it has wave-like properties and matter-like properties. So the question then remains, can matter or can particles behave like light? Well, in 1917, a PhD student in France, DeBroglie, was asking this very question. And he proposed a relationship between the matter and wave-like properties of things. And here's what his equation looked like. It said that the wavelength of anything, any part of any type of particle or anything, was equal to our Planck's constant, h, divided by the mass times the velocity. Well, again, lambda is our wavelength in meters, h is Planck's constant, m is the mass of the object that is moving, and it has to be in kilograms. And v is the velocity in meters per second. Okay, now, let's analyze what this means. All right, so the wavelength of something that's tiny, like photons or electrons, that wavelength is going to be much longer than the wavelengths for larger particles, such as, say, a baseball, which is going to have a much larger mass, and it's going to move a lot slower. So again, we're going to see tremendous differences in the wavelengths between subatomic particles and things that we're used to seeing in our macroscopic world. So let's go ahead and get started. I would like for you to calculate the wavelength in meters of an electron that's traveling at 1.24 times 10 to the 7th meters per second. So that's traveling really fast. Now, in atomic theory, we said that electrons didn't have mass, but in the physics world, I said it does, and that mass of that electron is 9.11 times 10 to the negative 28th grams. Now, Planck's constant is in joules times seconds, and a joule is equal to a kilogram meter squared per second squared. And because we have got to have our units cancel out, we need all of our masses to be in kilograms to match the kilogram that's in the joule in Planck's constant. So the first thing you need to do is get that 9.11 times 10 to the negative 28th grams into kilograms, and then you'll plug in your values, plug in your units, and watch how they cancel. So stop the video now and try to calculate the wavelength of an electron traveling at this speed, and then check your answer in the next slide. Well, here's the answer. The wavelength of an electron is equal to Planck's constant, remembering that a joule is a kilogram meter squared per second squared. So it's Planck's constant divided by the mass in kilograms of the electron. And when I converted the grams to kilograms, I got 9.11 times 10 to the negative 31st kilograms. And then I multiplied it by its velocity. So the answer is 5.87 times 10 to the negative 8th meters. Be sure that you've plugged these numbers into your calculator and make sure that you're getting the right answer and you're using the exponents correctly in your calculator. Okay, well, that seems like a short wavelength, 10 to the negative 11th meters. However, let's compare that to the wavelength of something in our macroscopic world, something like a baseball. So here's our second problem. Calculate the wavelength of a baseball that has a mass of 149 grams and is traveling at 41.3 meters per second. That's a pretty fast baseball, by the way. Now, the first thing you need to do is get that grams into kilograms so that all of your units will cancel. Go ahead and stop the video, work the problem, make sure that all of your units cancel, and then go on to the next slide for your answer. Well, this wavelength is much, much, much shorter than the wavelength of an electron. It's 1.08 times 10 to the negative 34th meters. And so you can see that the wavelengths in our macroscopic world and things that we're able to see with our eyes are so small that they're not even measurable. So, the conclusion from all of this and these calculations should show you that particles that are in our subatomic world behave very differently from our macroscopic objects that we're used to. They actually have a wavelength that is measurable. So we can envision electrons and photons and these particles having wave-like properties. So there were experiments done that confirmed DeBroglie's hypothesis and his equations. And Americans, Davison and Germer, along with a guy named George Thomson, yes, a relative of JJ, it was JJ's grandson, demonstrated that electrons could show a diffraction pattern, and so that was proving that electrons do indeed have wave-like properties. So,